Before we go there, yet across the gulf of space, minds that are to our minds as ours are to those of the beasts that perish, intellects vast and cool and unsympathetic, regarded this earth with envious eyes and slowly,
understand that quote
surely
now, don't you?
drew their plans against us. It's us. We are peering our eyes and our unsympathetic way of being onto Mars. And
now you got it.
So this is a timeline between Stan Keith, the hydrothermal geologist and president of Magma Chem Research Institute, and the Mars Curiosity rover. And it's interesting and part of the story because when Stan left America and went on this 5 to 7 year journey in Norway in the Barents Sea and studying the UDH process to the best of his ability with access to all the data he could possibly get on this rock in the subsurface, he was putting together his knowledge and all the anomalies he could find to create the UDH model, the ultra deep hydrothermal model for our planet. In 2020, discoveries were made, the model's completely put together, and now we're teaching the UDH course October 1st. We're teaching it week by week, anomaly by anomaly, into the details and how this model actually works. In the same timeline, which is really cool, the rover in 2012 was being launched to Mars. It lands, it starts discovering all kinds of data and the engineering and it's just everything about this story is incredible. So Stan's over there doing it on the planet. Mars rover is over there collecting all this data from the UDH process that Mars has captivated, and it sent all the data back. And now Stan has taken 3 months to dive into this data to understand and explain how the UDH process actually works universally and how, more importantly, it works on our planet to help us make predictions. And we're here, we're alive, and we're bringing it. Kerogen found on Mars, new oil generation paradigm today. If anything that gets exciting about Mars to me is the fact that you could potentially go there, drill a well, and find yourself a hydrocarbon deposit.
Right near the snake, by the way.
Is that where you would go?
I'll show you where I go.
Okay, hold on. Let's get this done. We're taking some left turns here.
Oil play on Mars.
All right. How old oil on Mars could have happened and how its formation helps us to better understand oil generation on this planet. This is someone finding kerogen on a meteorite in Africa.
On a fracture.
Fractured.
In a mineralized clast. And what it was a meteorite, and then in the meteorite they had heterolithic breccias. And in the fractures in the clast, on a fracture face, they did all this shit.
So you're making the connection that you definitely have kerogen on these meteorites. So kerogen on Mars isn't that hard to believe.
Right, but then we're finding it every unit that they've analyzed so far in the Gale Crater mudstones.
Yeah.
And in particular, these are lithologies where they are those laminated things. And when they sent all these guys in there, because this is expensive. They can't do that many of them. The machine Curiosity doesn't have, it might have another 10 or so where it can do, and then it's runs out of juice. Because it's got to do certain things to get those things ready to blast off.
Right.
With the libs. The fact that they've had it up there this long is absolutely way beyond anybody's expectation.
So, surprise, meteorites are holding kerogen and also have light hydrocarbons.
And then everything in the Gale mudstones that they've analyzed so far has it.
Has had it.
Yeah.
Hydrocarbon, kerogen and hydrocarbon generation.
So the bottom line is it's not that hard to find on Mars if you've got the technology to look for it.
And hydrocarbons are a very important and primitive process happening in our universe.
Yeah.
This is not some byproduct of this unique world we live in.
Yeah, not only that, this thing is, what's really important about this, as it was in the meteorite, because the meteorite was the same thing, they had chlorine in that too. And they had serpentine in it. on the fractures.
Mm-hmm.
So if you had a hydrothermal system that had chlorine, bingo.
Mud volcanism is a significant component to Martian geology. Mars is now a dead rock. There is no magnetic dynamo. There's a pesky perchlorate problem for everybody who wants to occupy Mars. This one is interesting. There's no life masking the geologic processes. So this is for us, it's a way to look at primitive, big processes that are happening on our planet, that are happening on rock planets around the universe.
Yeah, it's a real interesting comparison that it clarifies
For you,
what's going on this planet.
the magnetic dynamo of Mars disappeared when the outer core froze. 3.5-ish billion years. Okay.
You just love being an announcer.
Talk to me about this is a magnetic field map of the complete planet, and then they're also looking at from polar views.
Mm-hmm.
Wow. Cool. What popped out to you?
That's the Mercator view there. Well, okay, so you've got the blues, which tend to be the topographically low areas, non-magnetic. And then these red areas, which tend to be topographically high and magnetic. So these are your more things that we're trying to make themselves into. This is thicker crust.
Mm-hmm.
That's thinner crust.
Okay.
This is consistent with oceanic crust.
Okay.
That's consistent with protocontinent crust.
Wow. So you got essentially a continent, a big body of continent, and then oceans in between.
Yeah.
Brine oceans. Look at that. There's Gale.
Yep.
Which is the gravity low.
Yep.
Indicative of serpentinite diapir.
Yep.
Okay, and what else are you seeing in this gravity map then?
Well, it's seeing structure. So, I mean, your cracks of the world is coming like this.
Oh, man. Oh, man, Stan. This is one of the coolest things when we started talking about Mars, and you go, oh, Mars has got a funky big, wow. Yeah. Just like our plate tectonic equator. For those not familiar with how the plate tectonic equator was constructed, Stan Keith, one of the designers and developers and authors of Cracks of the World, how do you explain simply how the plate tectonic equator made?
Well, that was just something that came along at the end of this exercise. I mean, we didn't even have that as a concept until we had the map made.
Mm-hmm.
But then it was a sort of a easy observation to make, where you had everything north of it except for a few. There's one exception right there, where it's going right slip. But all of these are offsetting, especially this guy. That's a 2,500 kilometer offset.
To the left.
Yeah, to the left.
Bang, everything so.
And then that just goes all the way through the planet. And most of these big guys up here, they're all left steps. There's another big left step. These are left steps through the Caspian. Wow.
So and that's because the initial torque of getting our planet to start spinning.
Yeah, that ties into the torque on the spin axis. Spin axis introduces a planetary scale torque, to its surface fracture system.
That would put everything in a left lateral, right lateral divide.
Correct.
Real quick, I put in Gale.
Yeah, and that's a clear left step.
Bang, this guy right here.
Left shear. And you can see how that thing goes all the way along here.
And
that dot.
Gale is sitting right on the contact between continent and brine ocean on Mars.
Yeah, so this shear zone appears to be a structural boundary that was in left shear, just looking at the topographic fabric there.
Right. There's a big crack going right over the top of Gale. Here is a geologic map of Mars.
So here's that guy.
This is where Stan would put a plate tectonic equator on Mars.
Now, I don't know whether those are in right slip.
You drew this
But
line.
I know these are in left slip right there, right near where Gale is.
All right, let's talk sedimentary features and keep it in context with what we're talking about here. What are we looking at when we see these Mars photos?
A preserved mud mound.
18,000 foot tall?
Yeah, it's if you got to put the stratigraphy at the bottom of it together too. So I think the number is about 18,000.
Wow. Okay, here's that timing again.
3.7 to 3.8.
Mars, so
See, all these events go into that boundary between the Noachian and the Hesperian.
wow. The predicted petroleum system that's on Mars based on the data that we have.
I'll go with that.
Geologic implications for our planet at the end of the day. So at the end of this, we are going to just sum it up and say it's happening there. The rover's seeing it. The data is coming back. Here are the implications that we can learn from this data.
So what are they?
That's a good question. We're going to make it up at the end. At the end of the day, you got a hydrogenation process to make oil that doesn't have anything to do with life. That's a big one.
Yeah, origin of oil is a big one.
Origin of oil is a big one.
Importance of mud volcanism is another one.
Right. This process of rocks that are made from kind of an igneous sedimentary integration. It's weird.
Yeah, it's what.
It's weird.
See, mud volcanism on this planet is probably 50% of the so-called sedimentary rocks. And, and it's a really, really interesting question as to whether or not mud volcanism is a sedimentary process or some other kind of process.
Right.
Because when you say volcano, all of a sudden you're implying some kind of magmatic thing going on.
Right.
It's coming out of the inner planet.
Right.
Which it is. But once it breaches, so it's half and half.
Right.
Till it hits the ground surface,
You'd call it an igneous.
It's not igneous, so it's
Hydrothermal.
not melted rock.
Right.
It's mud rock.
Right.
And it ultimately, a lot of that is driven by serpentinization. See, that's what most of mud volcanism is at the end of the day, is it's some kind of drive that goes down to where the serpentines are. And it has to do with the volatiles that are generated as the product of serpentinization, which, everybody on this planet, and for that matter anywhere else, focuses on the serpentine rock, quote unquote, rock product, but not its brine product. And the brine product is the source of the mud product and the mud volcanic product.
Right.
That's been overlooked. And Mars takes the mask of the plate tectonics, water, and life, among other things, removes that so you can see what's going on with mud volcanism.
Wow.
Tied to now fairly common occurrences of serpentine on Mars.
Wow.
So the serpentine mud volcanic rock system is really what we're seeing on Mars that gives us clarification as to what's happening on this planet. And that what's happening on this planet, that particular process, is a lot more important than we've given it credit for.